Linear partial differential equations. Analysis and numeric assignment help. For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@mathassignmenthelp.com, info@mathassignmenthelp.com, or reach us at https://www.mathsassignmenthelp.com. Consider the operator A equals minus C, x, y2 in some 2D region omega subset of or equal to R2 with Dirichlet boundaries, U del omega equals 0, where C, x, 0. Suppose the eigenfunctions of A are un x, with eigenvalues lambda n, that is, equals a none, for n equals 1, 2, numbered in order lambda 1, lambda 2, lambda 3. Let g, x, x be the Green's function of A. If f x equals n none x, for some coefficients alpha n equals, expression in terms of f and un, the g, x, x, f, x, d2x equals, in terms of alpha n and un. B, the maximum possible value of. For any possible u, x is underscore 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 in terms of quantities mentioned above. Hint: min max use the fact from the handout that if A is self-adjoint, then A-1 is also self-adjoint. Problem 2. In this problem, we will solve the Laplacian eigenproblem minus y2u equals lambda u in a 2D radius 1 cylinder r less than or equal to 1 with Dirichlet boundary conditions u, r equals 1 omega equals 0 by brute force in Julia with a 2D finite difference discretization, and compare to the analytical Bessel solutions. Mathsassignmenthelp.com. Problem.
Returning visitor.
You will find the iJulia notebooks posted on the 18.303 website for Lecture 9 and Lecture 11 extremely useful. Note: when you open the notebook, you can choose Run All from the Cell menu to load all the commands in it. Using the notebook for a 100 by 100 grid, compute the 6 smallest magnitude eigenvalues and eigenfunctions of A with lambda I, ui equals eigs, ai nev equals 6, which equals sm. The eigenvalues are given by lambda I. The notebook also shows how to compute the exact eigenvalue from the square of the root of the Bessel function. Compared with the high accuracy lambda 1 value, compute the error delta lambda 1 in the corresponding finite difference eigenvalue from the previous part. Also compute delta lambda 1 for nx equals New York equals 200 and 400. How fast is the convergence rate with delta x? Can you explain your results, in light of the fact that the center difference approximation we are using has an error that is supposed to be tilde operator delta x2? Hint: think about how accurately the boundary condition on del omega is described in this finite difference approximation. B. Modify the above code to instead discretize y psi by writing A0 as minus GTCGG for some G matrix that implements y and for some CG matrix that multiplies the gradient by C, R equals R2 plus 1. Draw a sketch of the grid points at which the components of y are discretized. These will not be the same as the nx in New York, where u is discretized, because of the centered differences. Be careful that you need to evaluate C at the y grid points now. Hint: you can make the matrix M1/M2 in Julia by the syntax M1, M2. Mathsassignmenthelp.com. Hint: notice in the iJulia notebook from Lecture 11 how a matrix art is created from a column vector of x values and a row vector of y values. You will need to modify these x and or y values to evaluate R on a new grids. Given the R matrix RC on this new grid, you can evaluate C, R, on the grid by C equals RC caret 2 plus 1, and then make a diagonal sparse
New
matrix
visitor.
of these values by diam, reshape, C, prod, size C. C, using this A is almost equal to Y psi. Compute the smallest dash lambda eigensolution and plot it. Given the eigenfunction converted to a 2D nx times New York array U, as in the Lecture 11 notebook, plot U, R, as a function of R, along with a plot of the exact Bessel eigenfunction J0, K0R, from the C equals 1 case for comparison. Plot R nx slash 2 and New York slash 2 U nx slash 2 and New York slash 2 K0 equals so. Newton x dash Besselge 0 at x 2.0 plot 0:0.01:1 Besselge 0 K0 asterisk 0:0.01:1 slash 50. Here I scale J0 K0R by 1/50th. But you should change this scale factor as needed to make the plots of comparable magnitudes. Note also that the R array here is the radius evaluated on the original U grid, as in the Lecture 11 notebook. Can you qualitatively explain the differences? Problem 3. Recall that the displacement U, x, t, of a stretched string with fixed ends, U, 0, t, equals U, L, t, equals 0. Mathsassignmenthelp.com satisfies the wave equation where F, x, t is an external force density, pressure, on the string. A. Suppose that F, x, t equals G, x, e minus it, an oscillating force with a frequency omega. Show that, instead of solving the wave equation with this F, x, t, we can instead use a complex force F, x, t equals G, x, e minus it, solve for a complex U, x, t, and then take U equals U to obtain the solution for the original F, x, t. Suppose that F, x, t equals G, x, e minus it, and we want to find a steady-state solution U, x, t equals minus it V, x, it is oscillating everywhere at the same frequency as the input force. This will be the solution after a long time if there is any dissipation in the system to allow the initial transients to die away. Write an equation equals a self-adjoint. AVG that V solves. Is positive / negative definite / semi-definite? C. Solve for the Green's function g, x, x of this A, assuming that omega equals n pi / L for any integer n, i.e. assume omega is not an eigenfrequency, y. Write down the continuity conditions that g must satisfy at x equals x, solve for x equals x, and then use the continuity conditions to eliminate unknowns. Mathsassignmenthelp.com D. Form a finite difference approximation A of your A. Compute an approximate g, x, x in MATLAB by A\dk, where dk is the unit vector of all zeros except for 1/delta x at index k equals x/delta x, and compare, by plotting both, to your analytical solution from the previous part for a couple values of x and a couple of different frequencies omega, 1 pi / L and 1 pi / L, with L equals 1. Show the limit omega 0 of your g relates in some expected way to the Green's function of d2/dx2 from class. Mathsassignmenthelp.com Problem 1. A is self-adjoint under the inner product from class and the 1D version in homework, and hence the eigenfunctions are orthogonal for distinct eigenvalues, but not necessarily normalized.